All right, we are now recording. We'll go from current slide. We've already done example 4. We're going to be doing example 5, but it's not on the slide set. While the projector's coming on, I think I announced this last time, just a reminder. If you yourself or someone you may know is interested in a line worker training program that will be offered here at Lawson State Community College during the summer, June 8th through August the 14th. This is in partnership with Alabama Power and various utility and contracting companies. If you know of anyone who may be interested in participating in this, today's the last day to apply. Okay? They'll be accepting applications through today. The class will be meeting from June 8th to August 14th, Monday through Friday, 8 to 4. That's a 9-week program, 8 hours a day. So I imagine about an hour will be given for lunch. Program tuition cost is $4,150 plus fees, and the fees include books, PPE, which is personal protective equipment that you have to purchase or rent or whatever on your own. The CDL, that's commercial driver's license physical, you have to pay for on your own. If you're getting one of those, then I think it's probably required. And any other permits, licensing, or exam fees, that's also in addition, because not everybody will be taking the same permitting or licensing or exams. Okay? Scholarships are available. They're really looking to get people out there into the program, so scholarships are available. The program outcomes will include OSHA 10 certification. That sounds pretty impressive to me. That's Occupational Safety and Health Administration 10 certification. You'll come out with a commercial driver's license, CDL. You'll come out with cardiopulmonary resuscitation training, CPR training, and of course you'll come out with basic line worker skills. If someone does have questions and needs more information, contact information here at Lawson State is the Office of Workforce Development, which I think is located over in the Ethel Hall building. If not, it's probably over in Millsouth. I think it's in Ethel Hall. Dr. James Gray is the Workforce Development Manager. I have a phone number for him, and it sounds like this campus phone number. That's why I think he's over here. I have an email address, and then Mr. Tommy Hobbs, the Assistant Dean for Workforce Development, along with certain his office is over there. Okay, so to apply for the program, there is a link you go to, and you have to apply that way. Today's the deadline, so if you know of anyone who may be interested, they need to go through this link. So come copy the link, whatever, and give it to them if you know someone who may be interested. And I can't remember if I said this one or not. I think I did, but I know some of my classes I forgot to say it. This coming Friday, I will not be on either campus past 6 in the morning, okay? I'll be leaving around 6. We're going to Opelika for a mandatory meeting, a statewide meeting, and I won't be coming back until probably around 5 in the afternoon, so I will not. Huh? Sure. And in the morning? Sure, I thought you meant in the evening. Yeah, you could do that too. Well, I'm not going to hold my breath. Okay? All right. But, yeah. I may not be there quite at 5:30, but wait for me and I'll get there. Okay. And let's see. Christian came in, and did I want to mark him or not? I guess I have to. Okay. Good deal. Okay. Any questions on anything either we've done or any other stuff? Any questions? All right. We're in Chapter 3, Differentiation, Section 3.3. Now, for those of you who are in the old book, this is probably Chapter 2 and probably somewhere around 2.3, but you'll have to find that out on your own. The title of the section is Product and Quotient Rules in Higher Order Derivatives. We had done example 4, the one that's on the screen, but they didn't have 5 or 6 on the PowerPoint, so we're going to do 5 and 6 here. This is on our page 146. I don't know what page it'll be in the other book, but you can figure that out. Okay. Okay. Example 5. Find an equation of the tangent line. They're not just saying find the derivative now. Find the equation of a tangent line. Okay. To the graph of this function. Three minus 1 over x over x plus 5 at the point negative 1, 1. Now, cynic that I am, I want to make sure this point is this graph. Otherwise, I'll do a lot of work to find out the answer doesn't make any sense because it's not even there, okay? So let's first check and see if we put in minus 1 for the x, do we get 1 for the y? So here's the first x here. If you put a minus 1 in there, what does that? That becomes a minus 1. 1 over minus 1 is negative 1. 3 minus a minus 1 is, okay, 4. And the denominator would be minus 1 plus 5 is 4. 4 over 4, sure enough, is 1. So they did give us a problem that makes sense. Okay. Now, what we're looking for is the equation of the tangent line to the graph at that point. What do we need to know to give an equation for a tangent line? Or any line? Any ideas? Say again? Slope. We definitely need a slope. And what else? A point. And here's a point already. They already gave us a point. It's got to be on the tangent line because that's where it touches the graph. And we already verified that. So all we need is a slope. Now how are we going to get a slope out of this? Aha, we got it. Take a derivative. Okay? So let's do before I try to take a derivative of that, that's pretty ugly, isn't it? How could I rewrite this before I take its derivative? What is it that's messy about that? Second? Okay. Yeah, okay. That's one way of phrasing it. Fraction in the numerator, but also the other way of saying the variables in the denominator in the numerator, okay, which is the same thing. How do we make that look a little nicer? Because remember, I don't like having variables in the denominators if I can help it, okay? So how do we improve on that? Say again? Well, this isn't either a radical expression or anything else that really that would work or help you any. What's another way? I'll start with the 3. I'll even write down the minus. How could I write that 1 over x so it's not a fractional form? X to the negative 1. Yeah, x to the negative 1 over x plus 5. Now we still have a variable in the denominator, but there's not a whole lot I can do with that now. There is something I could do, but they don't want you doing that yet, okay? And it probably would be just as messy. So, what situation do we have here? This divided by that, what kind of rule? If we're going to be taking a derivative like JJ said. Quotient rule, okay? All right, so let's do f prime of x. And how does that quotient rule go? Low d high, so that's x plus 5. That's the low. What's the d high? Derivative of that numerator. Help me, somebody. I'm drowning up here. Derivative of the numerator. Second, x to the negative, what did I hear? Ooh. Negative 2. Because you decrease it by 1, right? When you take a derivative. Make sense? Okay. That's the low, d high. What's next? Okay, but something goes between it. Minus high d low. And what's your high here? 3 minus x to the minus 1. And what's d low? Derivative of the denominator. 1, yes, okay. And what's all that over? Low, which is x plus 5 squared. And we're going to leave it like that unless there's some reason to change it. Okay? But we've got some stuff we need to do in the numerator. For instance, we need to distribute that 1 over x squared, which is what x to the minus 2 is, across there. And what does that give us? X times 1 over x squared would be one over x. Okay, I'm going back to this form, or x to the minus 1, that works just as well. Okay, next. Plus 5 over x squared, okay, minus 3, right? And then the last term is second, plus 1 over x. Now I'm going back to that because I'm getting ready to evaluate, and it's a little easier to evaluate when you got them in the denominators. Okay, I hope anyway. All right, and all that is over x plus 5 squared. There's your derivative in pretty ugly form, but all we're wanting to do, we got the derivative. JJ wanted to take a derivative. I don't know why. How is that going to help us? Second? I can't. Okay, yeah, ultimately, but what is this going to do for us? Plug a negative 1 in for x, and that gives us the slope of that tangent line. Perfect, okay? So, f prime of minus 1 is going to be the slope at minus 1, and x equal minus 1. So let's plug that in, and we'll plug it into this form. What is 1 over minus 1? Negative 1 plus 5 over a negative 1 squared. What's that going to be? 5. Perfect. Minus 3 plus, and what's, ooh, there's another 1 over x. Let's just make this a minus 2 here then, all right? Just save ourselves a little bit of writing here. I'm so lazy, okay? And all that is over, what is negative 1 plus 5? Huh? Yeah? Okay, plus 4 squared is 16. All right. Feel like a dentist up here. Okay, pulling teeth. All right, what's negative 2 plus negative 3? Negative 5 plus 5 is 0. Uh-oh. There's the slope of our tangent line. Okay, is 0. And we have a point there, so what must be the tangent line? What formula do we use? Point slope. How does that go? Fill me in. Y minus y1, right, is equal to, I'm doing all the work here, point slope formula. How does this go? Okay. Slope is m times x minus x1. Okay. I thought maybe I showed you this before, but just in case you forgot. Do you remember the slope formula? How does it go? M is equal to y2 minus y1 over x2 minus x1. Okay? That's if we knew 2 points and we're getting a slope. If we know the slope and only 1 point, just take off the other point. Okay? Which would be taking off the sub 2's. Because we don't know that second point. And then multiply both sides of that equation by x minus x1, and you have y minus y1, that's the numerator here, is equal to m, that's over here, times x minus x1. There's your point slope formula right there. Now, what's your point? What's your point? Okay, so the y1 is 1 is equal, and what's your slope? 0 times, who cares, x plus 1. Who cares? It's still 0. So what does this give you as your equation of the tangent line? Y minus 1 equals 0. What's the equation of the tangent line? Y is equal to 1. Yep. Y is equal to 1. Let's see, did they do it right? Yeah, there it is. Okay, finally I found it. Y is equal to 1. Done. Now, unfortunately, I don't have this on the slideshow, but I will hold it up for you to see. It's a fairly weird-looking function. Okay. All right. We know it has a vertical asymptote of x equals 0. X equals 0. It can't be that. So the y-axis is the vertical asymptote. And also another one, x equals -5. There, that one is. Oh, this is heavy. It's sinking fast. Okay? And here's the point at -1, 1. I didn't graph it for you. I'm not about to, but I'll let you figure that out. You can do it on a graphing calculator if you got it. Or, it's not that hard to plug in. We know that point's there. We found out the slope is 0, so the tangent line is y is equal to 1. Constant function, y is equal to 1. Okay. Any questions on that? Okay, with that done, let's move on to example 6. And no questions? Need it out there a little longer? Okay. Got it? Okay. So let's do example 6. Not every quotient needs to be differentiated by the quotient rule. Thank goodness. I'm sorry, I didn't say that, did I? For instance, each quotient in the next example can be considered as the product of a constant times the function of x. Okay? In such cases, it's more convenient to use the constant multiple rule. Okay? So here's the A part of example 6. Y is equal to x squared plus 3x over 6. Do you need to use a quotient rule there? The answer is no, because that doesn't have a variable in the denominator. It only has a number. So how could we rewrite that to make it so much easier to take as a derivative? Pull out the (1/6). Just a number, right? Times x squared plus 3x. Isn't that the same thing? Yeah, same thing, okay? If you don't believe me, put this over 1 and multiply 1 times this is that, 2 times that, we'll get exactly that. Okay. It's the same thing. Can you take a derivative of this without using a quotient rule? What would that be? 1/6 times 2x plus 3. And if you wanted to distribute the 1/6, that would be a 1/3 x plus 1/2. There would be the derivative. I don't know if they did it. They didn't. They rewrote it this way. 2x plus 3 over 6. That's fine too. I don't care, okay? What's that? You can leave it just like that. Yeah, perfectly fine. In fact, all 3 answers are correct. And if you were doing advanced web assign, you better guess right. Oh, if you write one of those correct answers, but it's not looking for that correct answer, it's saying, no, you got it wrong. And you say, oh, I did my differentiation wrong. I did something. No, you didn't. You did everything correct. All 3 of those answers are perfectly fine. Okay? Let's look at the B part of example 6. What if you had this? Y is equal to 5x to the 4th over 8. Do you need to do the quotient rule? Yay or no? No. Why not? No variable in the denominator. You don't need the quotient rule. So how could you rewrite this? Five eighths times x to the 4th. And then can you take a derivative of that? What would that be? Say again? Okay, and can you simplify that any? Four is in the numerator, 8's in the denominator. What can you do with that? Five over 2 x cubed. Now, the way they did the last one, I would almost guess they will write that as 5x cubed over 2, which is just another way to write it. Nothing special, except they left it in the other form. So they're not very consistent, okay? They left it like we did it the first time. But that's another perfectly good answer that they could say, oh, now, WebAssign would be correct if you left it in this form. Or if you put it 20x cubed over 8, you haven't reduced that. So go on and reduce if you can. But otherwise, whether you leave it over one denominator or the fractional coefficient, it doesn't matter. Okay? C. That's yes in Spanish. Okay. How about this one? y is equal to -3 times 3x minus 2x squared all over 7x. What about that one? Do you need the quotient rule? What you think? Or do you think? I'm not sorry, I didn't say that. Okay, I like that idea. Let's start with that. And let's take out a -3/7. Okay, and what do you have left then? 3x minus 2x squared, I hope that is, isn't it? Over then you have something left? X. Okay. Do you need the quotient rule on that one? Yes, you can divide out an x. Okay. How do you want to do that? The -3/7, I understand. That's out there. What do you have left? 3 minus 2x. Do you need a quotient rule for that one? No. What's its derivative? Y prime. Using that. Did you say 6/7? Please say yes, okay? Okay, x, okay. Let's see if that is right. Okay? This times this is just going to be a constant. Derivative of constant 0. So the only thing you're doing is the derivative of this times that. Okay? This times that is positive 6x over 7. And then the derivative of that is positive. Oh, you don't need an x there, do you? Positive 6/7. Do you see that? Way simpler than anything else, okay? Positive 6/7. Does that make sense?
You won't do it last time?
Okay. I'll take it one more thing, distributing back in. It seems like we're going backwards here, but let's do it. This will be minus 9/7 when you distribute this across there, right? Okay. Plus, because minus times minus is plus, 6/7 x. Okay, then take a derivative of this. Derivative of the constant is 0. Derivative of that is 6. Whoa, easier. Way, way easier. Okay? Let's see if the book, the book got it right and wrote it in the right form. I can't think of any other way to write that one. Okay, good. Or 6 times 7 to the minus 1, or something like that. Webasound would go crazy. All right. I'm going to have to erase what I've done so far to do the D part. Is that okay? Y'all need this any longer? Anybody? You okay? All right, let's do the D part. Y is equal to 9 over 5x squared. Okay? Do you need the quotient rule to do that? Somebody help me. People are shaking your head without even looking because you know none of these you do. How would you redo that? Second? Okay. That sounds like a good idea. 9/5. What's left when you take that out? Second? It's 1 over x squared, isn't it? Because x squared is in the denominator. You can't just move it anywhere you want to, right? So that would be times 1 over x squared. That may be a little better, but I I wouldn't want to try to take a derivative of that without doing something else. Earlier, how were we taking derivatives of that? In fact, that last example, how do we do that? Anytime you have a variable in the denominator with a power, another way to write this. 9/5, second, x to the negative 2. Do you need a quotient rule to take the derivative of that? No. Okay, so what would be your y prime? Okay, I'll buy that 9/5 times x to the negative 3, but you have something in front of it. Negative 2. You have to do your exponent times your coefficient, which then I would write as minus 18/5 x to the minus 3, which I'm just going to make a guess. The book is going to say minus 18/5x cubed. Let's see if they did. Yes, I knew they were going to do that. Okay. You didn't have to, but you could have. I'm just as happy with this that they went back and put it in the form that it was to begin with no negative exponent. Both of those answers perfectly good. Okay? I guarantee you, WebAssign is either going to look for one or the other, but not both. Not that you're doing WebAssign. So if you give one, the wrong one, not that it's wrong. The other one from the one they're looking for, they would say it's wrong. All right, any questions on that? Man, I said they skipped example 5 and 6. They also skipped example 7. So we still got that to do. So any questions before I erase this? Everybody got it? Okay. Let's do example 7. We'll finally get back to PowerPoint sometime. If n is a negative integer, then there exists a positive integer k such that n is equal to minus k. Wow, what a surprise, okay? So by the quotient rule, you can write, please don't use the quotient rule then. They're doing all the work for you. Let me, d by dx of x to the n. We know how to do that, don't we? What would that be? What would it be? Please say we know how to do it. Okay. How do we do that? Pretty simple. There's no tricks here. How do we do it? Derivative of x to the n. N times x to the n minus 1. Yeah, that's all there is to it. What if n was a negative number? It still works. You don't have to go a negative k and then do stuff with that and do a quotient rule. Just do this. If n's a negative number, give me a negative number, any negative number. Negative what? 2, okay? If that was a negative 2, okay? If you're taking derivative of x to the minus 2, what would that be? There will be an x in it, huh? Negative 2, x to the negative 3. That's it. You don't need to do the quotient rule to get it, you do the same thing we did before. And guess what? That even works if n was a fraction or a decimal. A negative fraction or a negative decimal, it still works. The power rule still works. So you don't have to go back and do a, the quotient rule to get there. It works. It just works. So please don't go back and do it. They did this, and it just like was going around your elbow to get to your ear. I mean, why go to all that effort? Just do it. Do the power rule. Okay. So we shortcut that one. Let's go on to derivatives of trigonometric functions. Now, I'm making a guess here. You folks in the other book, this is not a section in your text, right? So you'll have, you'll go to chapter 5 to get it. And I bet you'll find it somewhere there. Okay? Probably very, very similar to this. Okay? If I can be a cynic here again, I don't think they write new books. They just take old books and shift them around some. And I think that, did I say that out loud? Okay. But how do we do derivatives of trigonometric functions? Now, we already know two trig functions derivatives. What are those? What's derivatives of sine? Oh, I know it was a long time ago. Huh? Derivatives of sine? Oh my. I'm going to have to talk to the Cal 1. Okay? Cosine. What's the root of cosine? Say again? Negative sign. Yeah, okay. I don't have to talk to that. Okay, no. Okay. So, we know those two. Okay? Now we can, they love using the quotient rule to find the derivatives of the four remaining trigonometric functions. So sometimes you don't have to do the quotient rule. Guess what? They don't. They just tell it to you. And this is as good as anything, but if you really, do you want to see the quotient rule and see how they got these, or you want to just take the word for it? You tell me. Huh? Do it? How they got them? Okay. Tell me what tangent is. D by dx. What is tangent? A trig identity. It's what? Ooh. Sine over cosine. Multiple choice. Okay. Sine over cosine. Okay. Now, that's the quotient, isn't it? So what's the quotient rule? Low, which is? I can't get my pen to write. Okay, cosine x second. Wait, tell me what the quotient rule is. Low d high. Okay, what's the derivative of sine? Cosine. Okay. Okay, what goes next? Low d high minus high, which is sine x. And what's the low? Negative sine x. Okay. Over low. Is that Jennifer low? No, okay, never mind. Okay, that's cosine squared x. Right? Yeah or nay? Now, what's cosine times cosine? Cosine squared x. And then minus times minus is plus. Sine times sine is sine squared x. And this is divided by cosine squared x. Well, what's sine squared x? What's cosine squared x? Who's that trig teacher? Sine squared plus cosine squared. What's that? Yeah? Well, I don't care what then it is. I want to know what it is. It's what? Someone say it? Sine squared plus cosine squared. Always. Why? Okay. So, Dennis up here. Okay. That would be 1 over cosine squared x. And what's 1 over cosine squared x? Secant squared x. And that's how you get derivative of tangent secant squared x. Okay? Now, what you were given me before, cosine over sine, would have been cotangent. So that's reciprocal of secant. And that would have wound up being minus cosecant squared x. Okay? You can do it if you want to, but it follows the same pattern. Okay? And then derivative of secant. Okay? Frankly, I wouldn't even use the quotient rule here, I don't think. Let's see. Okay? D by dx, all I was saying that. D by dx of, what's another way to write secant? In terms of sines and cosines. What is secant? You just told me. You just told me 1 over cosine. So I'm going to write that as cosine to the minus 1. Oh, no, we can't do that yet. We will be able to do it later, but we can't now. So we got to do quotient rule. Sorry about that. Okay. So that would be 1 over cosine x. I was going to use another rule, but we haven't gotten there yet. So using quotient rule, which is a little bizarre here, but let's do it. That would be, how does that go? Cosine x. And d high is, second? Yeah, low d high, but derivative of 1 is 0, right? So that goes away. Minus high, and what's your high? 1, and what's the derivative of cosine? Negative sine, okay, over cosine squared x. So this merely gives you, minus times minus is plus, that'd be a sine x. I'm going to split that denominator over cosine x times 1 over cosine x. And what in the world is sine over cosine? Tangent. And what's 1 over cosine? Secant. There you have derivative of secant x and secant x times tangent. Doing very similar things, only you're doing cosecant is 1 over sine. You'll come up with a minus cosecant x cotangent x. Okay? So there they are. We've shown half of them, and the other half could be done much easier. Okay? Now, what I want to do is erase my scratch so I can write something here. Okay? I'm going to write it up here. D by dx of sine x is equal to what? You told me before. We've used it several times. Cosine x. And d by dx of cosine x is negative sine x. Now this is just a little thing to note. It doesn't mean all that much, but your functions, sine, tangent, secant, their derivatives are all positive. Your cofunctions, cosine, cotangent, cosecant, Those derivatives are all negative. So that may be just a little thing you can put in the back of your mind to help you remember if it's a code, the derivative is minus. If it's just a function, the derivative is plus. I don't know if you find it helpful or not. You have to remember what the rest of it is. Derivative of tangent is secant squared, and so the derivative of cotangent is minus the cosecant squared. Okay? And derivative of secant tangent and derivative of cosecant is minus cosecant cotangent. Notice everything here on these are codes, and these are your functions on both sides. Here, of course, one's on one side. This is a sine, that's a cosine, that's a cosine, that's a sine. But you know those. But these may be helpful. It's up to you. Just something that I use to help remind myself. Okay? They did the tangent rule as a proof, but we've already done it, so we will move on from there. Any questions before I move on? You got it? All right, let's do example 8. Why do they already do some of it for you? Goodness gracious. Here's a function. Y is equal to x minus tangent x. What's its derivative? Y prime is equal to, or dy dx, or dy dx of y is, you tell me. Say again? What's the derivative of x? No. Derivative of constant is 0. Derivative of x is 1. So exponent's 1, coefficient's 1. 1 times 1 is 1 times x to the 0. X to the 0 is 1. That's 1. Okay? Minus, and what's the derivative of the tangent? See that? Secant squared x. 1 minus secant squared x. Okay. Didn't know it would be that hard. Okay, how about this one? Whoa, what rule are we going to have to use here? Y is equal to x secant x. What rule will we need? Okay, what rule are we using? See, this was subtracted. What is this? Okay, so what rule do we use? Product rule, exactly. Okay, and how does that go? Okay, 1 times the derivative of the other plus the other times the derivative of the one, right? Okay, so you start with whichever one you want to. Okay, 1, you take the derivative of x is 1 times secant x, right? Second derivative, you multiply it by the other function. So secant x plus yeah, what's that? Okay, so it would be 1, if you take the derivative of the first times the second, that would be 1 times secant x, plus x times the derivative of that. So that would be x times secant x tangent x. Now I have a feeling they're going to write it in the other order. Now let's see, sure enough, x times secant x tangent x plus 1 times secant x. That's it. You can clean that up a little, but I don't care. Let's see if they do anything. Yeah. They factor out a secant x, because both terms have that times. And then they put the 1 in front. I don't know why x tangent x. Secant x times 1 plus x tangent x. If this is what they're looking for, I probably wouldn't have gotten it, because I would have either left it in that form or put secant x times x tangent x plus 1. Same thing. Why did they change the order? I don't know. Okay? But it's a correct answer. Perfectly correct. Any questions? let's do the, whoa, there is no C, okay? And they skipped example 9. So let's go back and do example 9. All right. Differentiate both forms of this. Y is equal to 1 minus cosine x over sine x. Or you could have written this, I'm going to show you why. You could have written this as, because you have a monomial in the denominator, a binomial in the numerator, you can split the numerator, okay? Have 1 over sine x, agreed? Minus cosine x over sine x. Right? What's 1 over sine x? Cosecant x minus, and what's cosine over sine? Cotangent x. So that's why they said differentiate both forms. Okay? So let's start with the first form. Now, in this case, okay, in most cases, I say it's much easier to use sines and cosines. Except in this case, it's going to be a quotient rule. In that case, you don't have a quotient, so it's actually going to be easier using that. But we'll do them both, okay? So let's do, what rule do we need for this one? I gave it away. Okay, how does that go? Low, which is sine x. Second. What's your d high? Derivative of that numerator. Okay, so that's minus a minus, which is sine x. With me so far? And what's next? Second? Minus, okay. You caught me saying it too soon. And what's next? You did low d high. Okay. High d low would be 1 minus cosine x times cosine x. Okay, that's d low all over sine squared x. Now, let's see what we've got. Sine times sine is sine squared x minus, and there's, if you distribute the cosine across, so it would be a minus cosine x. You see 1 times that, okay? And then minus a minus will be a plus cosine squared x. Agreed or not? Okay? Over sine squared x. Now, is there anything in that numerator that looks like it might be sort of familiar and easy? What about it? You mean here? Okay, if you separated this and did this over that, minus this over that, plus this over that, you could do that for that term. How about just the numerator? Anything look like it might be convenient there?
Sine squared x plus cosine squared x is equal to 1.
Yes, is equal to 1. So that simplifies it considerably. So what we have is 1 minus cosine x over sine squared x. There is your derivative. However, it may not be in the most convenient of forms, so you could rewrite this as 1 over sine squared x, which is what? Kyle was trying to do kind of before, but I'm doing it now, minus cosine x over sine squared x. Okay? Now, if you want to get that into expressions that don't have denominators. What's 1 over sine squared? Co. Cosecant squared x. Now I'm going to rewrite the second one this way. Cosine x over sine x times 1 over sine x. Is that legal in most states? Okay? And what's cosine? Says minus. What's cosine over sine? Cotangent x. And what's 1 over sine? Cosecant x. And you thought you were through with those trig identities, didn't you? No, you're not. Okay. Now, let's take y prime of this. This is y prime, by the way. Didn't do that. So y prime of this one, what's the derivative of cosecant x? Negative cosecant x. Wait, wrote it wrong. Okay. I said it, but wrote it wrong. Cosecant x. Continue. Negative cosecant x. Wait. Yeah, times cotangent x. Okay. Then what's the derivative of negative cotangent x? Positive. What's that? Cosecant squared x. And let's see. That's exactly what we've got down here. So who said it was easier to go to sines and cosines? No, if you can remember your derivatives, it was easier to do that side than do this side. Usually, if you have to use the quotient rule, find the number. If you can figure out a way to avoid the quotient rule, it's usually quicker. But sometimes you can't. So go with what you got. They are the same. Does that make sense? Okay. Now, no questions? Move on? All right, here we are. The summary below shows that much of the work in obtaining a simplified form of the derivative occurs after differentiating. Okay? I guess. Note that the two characteristics of a simplified form are the absence of negative exponents and combining like terms. We'll always combine like terms if you can, but if you do need to get rid of negative exponents as well. But negative exponents are far easier to differentiate. So put them in there and do it, and then they say go back and take them out. They say that's part of simplifying. I'm not too sure of that, but it's okay. So here's this one. They haven't even told you the function. Okay, it's fine. But I guess it's one we probably we haven't even done it before. If this is what you get after you differentiate, I'll tell you what the function was. It was 3x minus 2x squared times 5 plus 4x. It was a product. Because this is the product rule. The result of the product rule. Okay? Yeah. So, if this is what you get after you differentiate that product, which is of course this, then distribute, and you get, they've left out a bunch of terms here, steps here. So let's go on and fill in the steps. Distribute first, and that gives you what? And you distribute the 4 over these two. What do you get? 12x minus what? I thought that's what you said, 8x squared. Okay, now this one we got to do some foiling, right? So the first are plus 15. Then the outer is minus 20x, right? The inner is plus 12x. And then the last are minus 16x squared. Perfect. Okay? Now combine like terms. That's what they were getting at. Minus 24x squared. Got it. And here you have 12x and 12x is 24x. Minus 20x would be plus 4x plus 15. Yeah, that's how they got it. Make sense? Okay. Oh, this was example 1. Okay, I'm sorry, I didn't even notice this. Example 1 back there, that was what we had. Example 3 was the product of, well, you can go back and look and see what it is. This is what you got at the differentiating. So it's all right for me to go on and erase the first one because it's just going to get messier. Okay? All right to erase? All right. So this is what you got when you did example 3. Now, every now and then they'll put a vertical bar here. It's not in the book. It's not anywhere else. I don't know how the graphics guy did it, but if there's a vertical bar, it doesn't mean anything. It's just extraneous. So this will be a minus 2x sine x. And this will be a plus 2 cosine x. And here's a minus 2 cosine x. Hey, minus 2 cosine plus 2 cosine x minus 2 cosine x adds a 0, so it leaves you at minus 2x sine x. Yeah, combining like terms, they disappear. Okay? Example 4. This was the quotient problem. It was this in the denominator originally, and the numerator was this. Okay? Yeah. And then you're taking a derivative. So what you do, distribute first 5x squared plus 5 minus 10x squared. So 5x squared minus 10x squared is minus 5x squared. That works all right. Okay? And this will be a minus of minus is plus 4x. And so you got a plus 4x there. And this had a plus 5 and the other didn't. So yeah, you combine like terms. Okay? Another quotient problem from example 5. We did this before, so it's nothing new. 3x squared on this side. And over here we're going to have a minus 6x squared. So that's going to be a minus 3x squared. That's good. So let's do our x terms. This will be a plus 15x. This will be a minus 15x. Those add to 0. This will be a minus 2x. Whoa! Oh! Minus and minus is plus 2x. So you get a plus 2x there. Don't do them too fast. And minus times minus is plus. 1 times 5 is 5. Over this thing squared. And then the one we just did, sine times sine is sine squared. Minus 1. Minus cosine x. Plus cosine squared x. Sine squared x plus cosine squared x is 1. And then you have a 1 plus cosine x. We had already done all this. Okay? This is just showing combined like terms. They didn't deal with any negative exponents in that at all. So why they even mentioned it, I don't know. All right. Any questions on this? Need it any longer? Let's move on to higher order derivatives. Can you take a derivative? Sure, it's just a function. So just as you can obtain a velocity function by differentiating the position function, you can obtain an acceleration function by differentiating the velocity function. That's physics, okay? That's why Isaac Newton developed calculus. So he could do this kind of stuff, because before calculus, you couldn't do that. You just came up with approximate things. You could get it exactly. Another way of looking at this is you can obtain an acceleration function by differentiating a position function twice. Differentiate it the first time to get velocity, the second time to get this. So if you start with a position function, take a derivative, you get a velocity function. Take the derivative of that derivative, and you get the velocity, derivative of velocity, which is the acceleration. So the acceleration is the second derivative of position function. But guess what? You got to take them one derivative at a time. You can't combine, okay? So, not a big deal. The function A of t is the second derivative of s of t and is denoted by s double prime of t. Now, there is another way to write that, and I'm sure they're going to come up with it in a minute. I don't know why they don't do it now, but they'll come up with it. The second derivative is an example of a higher order derivative. You can take a third derivative, fourth derivative. At some point, some of them may become just zeros, and you don't need to do it anymore. Other times, they just keep on going. You can define derivatives of any positive integer order. 17th derivative. Okay, yeah, okay. For example, the third derivative is derivative of the second derivative. And the second derivative is derivative of the first, which is the derivative of the basic function. Okay. Here's other ways to write it. Okay? Higher order derivatives are denoted. First derivative, we already know y prime is one way, f prime is one way, d by dx of y, or dy dx is 1, d by dx of f of x is 1, or that one that we haven't used yet, but they keep showing us, is capital D sub x of y. In other words, this is the derivative operator, and the sub means what goes into the denominator. And you're taking this of y, right here. So d by dx, that's d sub x of y. Okay. Now, your second derivative, you could write it as y double prime or f double prime. Both of those are fine. Here's the next one. d2y over dx squared. And you might say, wait, why do you put the squares in different places? And here's one way to look at it. A derivative is a d by dx, right? And if you're taking a d by dx of a dy dx, then look. The d's look like they're squared, and the dx's look like they're squared. So that's why it comes out like that. Okay? Get used to them. They're there. Okay? Or you can say d2, it's hard to, I can't say my d by d. Okay. D squared by dx squared of f of x. That's basically, instead of y, you're putting f of x there. I would put it up here, but you can put it either place. Or this one, just because, like I said, this is your d by dx of d by dx, which is d by dx squared. This thing, d by dx of dy dx, or d by dx is d of y. Okay? Third derivative, y triple prime, f triple prime, d3y dx cubed, d3 by dx3 of f of x, or d sub x cubed of y. Or of f of x, you could put f of x in there too. Now here's something where it changes. After a while, if you just keep putting tick marks, and you have 17 tick marks, it's going to be hard to figure out what, whoa, is that 17 or 16? You know, it's hard to count, okay? So after the third one, start putting it in parentheses. Now why in parentheses? Then parentheses there, you think it's y fourth, y raised to the fourth power. No. If it's in parentheses, that means derivative. Fourth derivative of y. Or fourth derivative of f of x. Or this stays the same, d4y and d4. That stays the same, and that stays the same. It's only with your tick marks. Don't do any more than 3 tick marks. After that, put them in parentheses. And the nth derivative would be y, and even if n was 3, if you don't know what it is, you put it in parentheses. The nth derivative of f in parentheses of x, dn y over dx n, dn by dn y. D to the nth over dx to the nth of f of x or d sub x to the nth. Lots of ways to write them, and frankly, I don't even know why. Now, just to give you a little historical perspective, remember Isaac Newton developed this stuff? This is called, the d by stuff is called Leibniz notation. Newton didn't use that. Newton was more interested in positions, velocities, acceleration. He's a physicist, okay? So what he used was the dot notation. He used y dot, y double dot, y triple dot. People started making fun of this because they called it fly speck notation. Because not always is the paper all that neat and clean and pretty and white like we have, and it might have a dot in it, a fly speck, and you think that might be a derivative. So they made fun of it. So they don't really use this anymore. But occasionally in physics, you'll see a derivative with respect to time is done as a dot. So just hang on to that concept. That was Newton's notation. And they made fun of it and called it the fly speck notation. All right, enough of that. Here's example 10. Because the moon has no atmosphere, a falling object on the moon encounters no air resistance because there's no atmosphere there. In 1971, astronaut David Scott, he was either the third or fourth or fifth or something like that person to walk on the moon. Armstrong and what was the other guy's name? Neil Armstrong and second. Oh yeah, Buzz Aldrin were the first two to walk on the moon, and it was either the next Apollo or the one after that. Some subsequent one, David Scott walked on the moon, and he did the classic illustration of dropping a hammer and a feather at the same time on the Earth, which hits the ground first. The hammer, of course, but that's only because of air resistance. The feather has a lot more air resistance than the hammer does. Okay? But on the moon with no air resistance, you drop them, and guess what? You get it the same. No question about it. Okay? Now, the position function for each of those falling objects was then S of t is equal to negative 0.81 t squared plus 2. Now, I'll tell you a couple things without reading the rest of it. This is in SI, meaning for metric notation. What this is 1/2 of the acceleration due to gravity on the moon. Not on the Earth, on the moon, because that's squared. And he dropped them, meaning no initial velocity. The initial velocity was 0, so there's no t term here. And the plus 2 means it was 2 meters above the ground, which is about this, okay? It's about 2 meters above the ground. So that is where that came from. That's how I knew it had to be SI notation, not U.S. customary notation. So there's the thing. For S of t is the height in meters, okay? T is the time in seconds. Now, the question says, what is the ratio of the Earth's gravitational force to the moon's gravitational force? I know how they want us to do that. Okay, yeah, they've already given us that, and I was just going to ask that. Does anyone know what the S of t was if you're dealing with the Earth? Okay, that's what the acceleration due to gravity is. This is 1/2 minus 1/2 gt squared plus v0t plus s0. Okay, that was the formula we had before. And if this g is 9.8 meters per second squared, half of that would be 4.9. So this would have been negative 4.9 t squared, and with v0 being 0 plus 2. Okay? So that's where we're starting from. Okay? 1/2 of the 9.8 because of that formula. Okay? So, how do we get back to the acceleration due to gravity? That's what they're asking about. What is the ratio of the Earth's gravitational force to the moon's? Now that's, there's no force in this, okay? These are accelerations. So this should be of Earth's gravitational acceleration. is what they meant to say. But they're mathematicians, not physicists, so they don't always get it right. Okay, that's what they're asking for. Okay. Well, how do you get there? How do you get back to G by itself? You take one derivative and then another derivative. Okay. So let's take the first. S of S prime of t up here would be what? Negative 9.8 t, right? And S prime down here would be (1.62 t). You can stop right there because this is your acceleration due to gravity on the Earth. There's the acceleration due to gravity. So what's the ratio of those? Earth's gravitational acceleration to that of the moon's is 9.8 to 1.62. Someone pull out a calculator and see what that ratio is. Anyone got a calculator? All right, you got it. Good. What you got? Approximately. 6.05? Okay. I would say approximately 6, maybe. Okay? 6 times the acceleration of gravity on the Earth as it is on the moon. Other way, we usually say that the moon has 1/6 the gravitational force. Let's see how they did it. To find the acceleration, differentiate the position function twice. But you know you can only do it once and you got it. But we'll do it twice. Negative 1.62 t. The second time just gives you negative 1.62. If you do the same thing for the Earth, because the S double prime of t is minus g, acceleration due to gravity on the moon is 1.62 meters per second, and we know on the Earth it's 9.8, and when you do that, you get 6.0. Now, they rounded poorly, but we'll give it 6.0. Okay? Got it? Say again? Okay. Oh. Take the derivative of this, exponent times coefficient. Right? Got it? Does that answer it? Yeah. And then you take it a second time and you lose the t in both cases. So that's why do it a second time? You know you're going to lose the t. Except I was cheating. I was just being lazy. Make sense? All right. So they got the same thing we did, about approximately 6 times. The Earth's gravitational pull is about 6 times that of the moon's. Whoa! They have that as the last example, and sure enough it was. Homework exercises here would include any of the odds 5 through 9. And by the way, there's a concept check at the top. I usually don't mention those. A nice thing to read through, think through, make sure you understand. If you don't understand it, go back and find it in the text, okay? So, but once you do that, then the actual problems or exercises, any of the odds 5 through 9, they're all at Calc Chat, 5's at Calc View, 11 through 15, all at Calc Chat, 11's at Calc View. Any of the odds 17 through 23, they're all at Calc Chat, 21's at Calc View. 25 through 29, they're all at Calc Chat, 25's at Calc View. Any of the odds 31 to 41, they're all at Calc Chat. Any of the odds 43 to 59, they're all at Calc Chat, 43's at Calc View. 61's at Calc Chat. 63 or 65 should both be at Calc Chat. Any of the odds 67 through 73 should all be at Calc Chat. 75 or 77 should be at Calc Chat. 79 and 81 should both be at Calc Chat. 79's at Calc View. 87 83, I can't read, should be at Calc Chat. So should 85, so should 87. And then you can do any of the odds, 89 through, whoa, it keeps on going, 89 through 95. They should all be at Calc Chat. Then 97 through 107 should all be at Calc Chat. 97 should be at Calc View. 109 and 111 are both at Calc Chat. 109 is at Calc View. 113 and 115 are both at Calc Chat. If you want to explore doing 117 and or 119 and or 121, they should all be at Calc Chat. Then you got problems 123 through 127. Those odd ones should be at Calc Chat. 129 should be at Calc Chat. 131 should be at Calc Chat. Goodness gracious, they go on and on. 133 at Calc Chat. Either 135 or 137 should both be at Calc Chat. There's some true false here. 139 through 143 should be at Calc Chat. And then there's a proof. 145 should be at Calc Chat. All right, any questions? Boy, they love the home exercises here, don't they? Okay, let's discard those and now go to 3.4. All right. We have, what, 13 minutes? Yeah, okay. Let's do what we can in 3.4. All right, still in Chapter 3, differentiation. In your book, it'll be Chapter 2. Okay, and 3.4 is talking about the chain rule, one of your favorites of all times. It will soon be, I think. Okay, we'll find the derivative of a composite function. You remember when you did this in pre-calculus algebra, and you thought, why in the world is it making us do this? Is there something else just to have to remember? Now we'll see why. Because we run into those in calculus, and the chain rule is built to do composite functions. We'll find the derivative of a function using the general power rule, as if we haven't already done that. We'll simplify the derivative of a function using algebra, as we've been doing, and we'll find the derivative of a transcendental function using the chain rule. That for you will be in Chapter 5. For the rest of you with this book, that will be in this chapter, of course. Oh, and we'll also find the derivative of functions involving natural logarithmic functions. Again, for you folks, that will be in Chapter 5. And we'll define and differentiate exponential functions that have bases other than e, and that, of course, is in Chapter 5 as well. Okay, because those are transcendental functions. So, what in the world is the chain rule? We've yet to discuss one of the most powerful differentiation rules, the chain rule. We talked about the addition rule, subtraction rule, the power rule, and the product rule, the quotient rule. The chain rule, though, is one that's really important. This rule deals with composite functions and adds a surprising versatility to the rules that we've already discussed. In fact, when I was saying if you can avoid the quotient rule, the chain rule will let you do that sometimes. And usually a little bit better. Not always. Sometimes. For example, compare the functions shown below. Those on the left can be differentiated using the chain rule, and without the chain rule, and those on the right best differentiated with the chain rule. We haven't gotten to it yet, so don't sweat it if you don't know. Certainly, no problem here. What's the derivative of x squared plus 1? 2x, yeah. What's the derivative of sine x? No sine x. Derivative of 3x plus 2. 3. Okay. Derivative of x plus tangent x. Ooh, a little more thought here. 1 plus 1 plus 1 plus secant squared. Okay. You can do those without a new rule. What about this? Oh. No. This is a function within another function. That's what we mean by composite function. Can't do this without the chain rule. Okay? Sine of 6x. Well, we know it's going to start as cosine of 6x, but then there's another piece to it. Okay? This one, you can do it without the chain rule. If you expand that and do 3x plus 2 times 3x plus 3 times 3x plus 2 times 3x plus 2 times 3x plus 2, multiply all those together, and then use your polynomial rule. Any of you want to do that? No, I don't. Okay. There is an easier way with the chain rule. So, this one, ooh, it looks so similar here, except you got the x squared. The first part's going to be the same, 1 plus secant squared of x squared, but that you're not through because you have to deal with the x squared in the as a composite function. Basically, the chain rule states that if y changes dy du times as fast as u, and u changes du dx times as fast as x, then y changes du dx times as fast as x. Yeah, that's how I like to remember it. No. That is all true, by the way. But is that an easy way to remember it? Not in my book, okay? But we'll see there is a much easier way to do it. But that is true, and that is what it's saying. If you can figure out what it's saying. Okay. And here they're going to do that very same thing. A set of gears is constructed so that the second and third gears are on the same axle. Okay? So here's gear 1, you're cranking away at that. Okay? And here's gear 2 that you're moving when you crank gear 1. Okay? And axle 1. And then gear 2 moves around, and it's on the same axle with gear 3, and that cranks away and turns gear 4, which is on axle 3. Okay? I know y'all run into this all the time. Okay? Actually, if you ride a bike with multiple gears, you really are doing a little bit of this, not this much or something. Okay? So, as the first axle revolves, it drives the second axle, which turns in turn drives the third axle. So that's what we're focusing on, the axle spins, though we have to deal with the gears too. Let y, u, and x represent the numbers of revolutions per minute of the first, second, and third axles. So that's what we're looking for. Revolutions per minute of the first, second, and third axles. Now, dy du is how many revolutions y has per revolution of the second. How many revolutions of the first per revolution of the second. Now, if you think about this, what you have to do, and this is hard to do it, you count teeth, okay? These teeth, okay? Let's start with this one that's in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 teeth. That's strange, but it is. So let's start with this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Oh man, I can't see the teeth under there. But actually, it goes by diameters or radii as well. So they're going to tell us this in a bit, okay? And then, so the point is, to get this one to turn once, you have to turn this one several times. And the ratio is by teeth, you know, because to turn this once is going to be 11 teeth. So this one would be, let's do it this way then. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. one turn of this gets you to there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 gets you the second turn, and I'm just going to say 3. So I think it's going to be 3 turns of this for every, no, 3 turns of this for every turn of that. Right? Looks like it makes sense? Okay. So that dy du is going to be 3. 3 revolutions per minute of y for every 1 revolution per minute of u. Du dx, okay, u is this one or this one. Well, let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 again. Probably it's the same size. This one will be, let's start with this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Yeah, that's all it is. So the u dx is going to be 2. Because this has turned twice for every, this turns twice for every 1 turn of that. Because there's exactly half as many teeth. Okay? So the du dx is going to be 2. So du y dx would be the product of dy du times du dx. Now I know probably if you're really paying attention, you think, oh yeah, you just cancel out the du stuff. And indeed, that's what it looks like, and you can get away with it. You're not canceling out. This isn't really a division, but it's sort of like that. So this would be 3 times 2 is 6. So there's 6 turns of this one for every 1 turn of that. That's a 6-to-1 ratio. Okay. They're saying because the circumference of the second gear is 3 times that of the first. Yeah, I could tell that, couldn't you? That the circumference here, I can't tell. I could count teeth though, and that gave me a general idea. Is 3 times that of that, and the first axle must make 3 revolutions to turn the second axle once. So dy du would be 3 to 1. Similarly, the second axle must make 2 revolutions to turn the third axle once. So that's going to be du dx is 2, and the product of those is, combining those 2 results, you know that the first axle must make 6 revolutions to turn this one once. Y is 6 times the axle, okay? Because you just multiply those 2. So you can write dy dx is equal to the rate of change of the first axle with respect to the second times the rate of change of the second axle with respect to the third, and this will be the rate of change from the first to the third. Okay? And that's what we're getting at. Okay? It's the multiplication. Okay? Now, so dy du times du dx. And if it looks like you're canceling out those, you really aren't, but it does look that way, and that's a good mnemonic device to keep in mind. Okay? Don't tell a math person that's what you're doing. Okay? All right. Don't tell. All right, 3 times 2 would be 6. All right. The rate of change of the first to the third. In other words, the rate of change of y with respect to x is the product of the rate of change of y with respect to u times the rate of change of u with respect to x. It works out. I don't know how many times they're going to say it different ways. Example 1 illustrates a simple case of the chain rule, and that general rule is stated in this theorem and how we do it on time. Huh? It's what? 11:40. Sorry about that. We'll pick up with the chain rule next time. Did we get far enough along to do any homework exercise? That's the important question here. You're going to like the chain rule, I think. It's really very useful. It's a long section, though. Now, let's just hold off and just do those homework exercises for the other. And I believe a few of you still have a test you're working on, don't you? Yes, okay. I should maybe mention that I've received 6 in, that leaves me 4 out. So please go on and be working on those. We won't need them for a while, but we will need them at some point. I want you to have those in before I pass out the next test, which is still a ways off.
That's after we finish chapter 3, right?
What's that?
You do that after we finish chapter 3, right?
Yeah,
Makes sense.
yeah. I'm not going to do all of them. There's like 8 or 9 sections in 3. We're not going to do them all. We're getting closer, though. All right. Good deal. We'll end this